All right, hello. Welcome back. And now we're going to start the last section, which is section E of chapter 7. And this is dealing with counting and probability. Now, up until this time, we've dealt with very simple situations, simple experiments that we're able to figure out what the sample space is, or we're given the data and we're able to use the rules or the definitions of probability to calculate the different probabilities. And we can do that by either knowing the sample space and being able to count things, right? But what if you have millions of possible outcomes, right? What if you want to find out, you've got a birth order of 5 children, okay? You're going to be dealing with a lot of possible combinations. It's going to be tedious, if not impossible, to figure out all the possible combinations or possible arrangements. So we've got some other counting principles. We've got other formulas, other ways of counting properties and formulas that we can use to figure out what those numbers are. Because remember, in probability, we've got to just figure out 2 numbers. The number of possible outcomes that give us the number of outcomes that give us a particular event that we're interested in. And the other number is we need to know the total possible outcomes in the sample space. Okay? So, one of the rules that we use is in a case where we have n choices, if we are going to make our selections out of those n choices, we can figure out how many different arrangements are possible by using what I call the fundamental counting principle. And so in this case here, we basically take, of the n choices, we're going to make our selections, and we can make n to the r different, oops, that's not writing. Huh. Wonder what happened. Anyway, it's not, my pen's not writing for some reason. Okay, so here we go. Here's an example. It says, how many 7-number license plates are possible? Now, this assumes that we can have repeats, right? We're repeating digits. So if we have a 7-number license plate, and we want to know how many different possible license plates we can have, we look at each position of the license plate. And in the first position, we have 10 choices, right? The digits 0 through 9. And then, of course, with the second place, the second digit, we have 10 choices to choose from. And so for each choice, for each position on the license plate, we have 10 choices to choose from. Okay? And so since there are 7 numbers, then we basically take 10 times itself 7 times. And so there are 10 million different possible license plates. Now, the fundamental counting principle basically just says, look, all I have to do is take all of the different arrangements, or excuse me, all I have to do is, of all the different categories, however many distinct items I have to choose from in each one of the categories, if I want to know how many different arrangements of those categories I have, by only selecting one item from each category, then all I do is take the number of items in each category and multiply them together. Okay, so what we just went over is a specific example of the fundamental counting principle. Okay, now permutations are different. Now, when we're dealing with permutations, and in fact, permutations is a type of an arrangement. Okay, but there's a couple of differences than using the fundamental counting principle. It does use the fundamental counting principle, as you're going to see, but whenever we have the following, we're dealing with permutations. So all selections come from a single group of items. No items may be selected more than once. And order matters. Okay? So the arrangement of the items matter. So order matters. And the total number of permutations that's possible for a group of n items is n factorial. Because what you're doing is you're arranging all n items. Okay? So this symbol, the exclamation point, is called a factorial symbol. And that n factorial means that we take each integer from n all the way down to 1 and multiply them all together. Okay? And that will give us the total number of permutations. Okay? So now let's look at an example. So a middle school principal needs to schedule 6 different classes. So we have algebra, English, history, Spanish, science, and gym. So there are 6 different time periods, right? So we're going to fill in each one of the time periods with one of the 6 subjects, 6 classes. And the question is how many different schedules are possible? Well, since we have 6 time periods, and we can only put one class in each time period, then the way we do that is we use 6 factorial. And just think about it this way. The first class, the first period, how many classes do we get to choose from to put in that first period? 6. And then what about the second class period? Well, once you fill the first class period, well, now you only have 5 to choose from for the second class period. And after you choose one for the second class period, the third class period, you only have 4 classes to choose from, and so on and so forth. And so if you take all of those periods, and you fill them in with a number, right? 6, 5, 4, 3, 2, and 1, then the fundamental accounting principle just says multiply them all together, and that's your answer. And so 720 different schedules are possible. Now, here is the formula for making any kind of selection that's less than n. Okay, so let's say you wanted, instead of choosing all of the items, let's say you want to just choose a subset and you want to make an arrangement, you want to find all the different possible arrangements of r items out of the total n items. And so this permutation formula will give you that answer. But again, you don't even need to remember the formula, because if you just remember just filling in the blanks with numbers and then using the multiplication rule, or not the multiplication rule, the fundamental accounting principle, you'll get the right answer. Okay, so when we say NPR, that's the number of permutations of n items taken r at a time. Okay, or another way of saying is the number of permutations when we're choosing r items out of a total of n. How many different ways can you choose r items out of n when order matters? So let's look at this one. So we've got on a team 10 swimmers. How many possible 4-person relay teams are there? Well, in this case, order matters on the relay team, because you've got a person that goes first, second, third, and fourth, right? So the order matters. Now, how many possible 4-team positions, 4-team relay teams are possible? Well, in this case here, we've got how many choices to choose from for the first position? Well, there are 10 swimmers, so we get 10 to choose from. After we've chosen that person, for the second position, we have 9 to choose from. And then for the third position, we'll have 8. And for the final position, we have 7. So again, the fundamental accounting principle just says multiply all those numbers together, and that's your answer. Now, the cool thing is the permutation formula will give you the same answer. Okay, let's look at awards. If an international track event has 8 athletes participating in 3 medals, gold, silver, and bronze, are to be awarded, how many different orderings of the top 3 athletes are possible? So again, order matters in this case because you've got bronze, silver, and gold, and so only one winner will get each of those awards. Okay, so order matters. So now if we have 8 athletes and we're going to choose 3 out of the 8, right? So only 3 out of the 8 will get an award. Then we want to know, hey, how many different ways can we have 3 out of the 8 athletes get gold, silver, and bronze? Okay, again, all we have to do is pick, we have 3 spots to fill, right? A spot for gold, a spot for silver, and a spot for bronze. So for the spot for gold, how many athletes are possible that would get gold? And that's 8. And then once the gold is filled, then how many athletes are possible or to choose from that can get silver? 7. And then finally, we have 6 left over that could get bronze. And so again, all we do is take the 8, 7, 6 and multiply them together. But as you can see here, the formula reduces to the exact same thing. So we get 336 different orderings for the top 3 athletes for bronze, silver, and gold. All right, let's look at Little League batting order. So a Little League manager has 15 children on her team. How many ways can she form a 9-player batting order? So order matters in this case because you have a lineup, a batting lineup, right? So how many different ways can you have a batting lineup, batting order of 9 players out of a total of 15 children on the team? Well, again, you've got 9 spots to fill, and so you're going to choose from the 15. So you're going to have, it's going to start with 15 all the way down to what? So you have 15 times 14 times 13, 12, 11, 10, 9, 8, 7. And if you multiply all of those together, you get this answer. 1,816,214,400 possible batting orders. Okay. All right. All right, let's keep going. Now, the big difference between combinations and permutations is what if order does not matter? So if we look at combinations, they very similar to permutations. So again, all selections come from a single group of items. No items may be selected more than once. And in this case, order does not matter. So now, when we're dealing with combinations, the formula is slightly different. Okay? So this is the formula for combination. Notice that we have the extra r factorial in the denominator, and that is to get rid of all of the orders. We have to divide out all the orders from size 1 all the way to size r. Okay? And so this is the formula. Now, the easiest way is just to take, once you know how to find permutations, again, you don't need the formula to find permutations, but to find combinations, all you have to do is find the number of permutations and then just divide by r factorial. That's the easiest way I've been able to find of doing it without a calculator, okay, or without plugging in, chugging in a formula. Now, what this reads is n choose r. So it's the number of combinations of size r chosen from n objects. Or the way they say it is the number of combinations of n items taken r at a time. Which to me doesn't really make much sense. I like the way I say it. So let's look at committees. We have a committee of 3 people are needed out of 8 possible candidates. And there are not in any there's not any distinction between the committee members. So there's not like any kind of ordering to them, right? And the reason is because all we care about is whether the person gets chosen for the committee. We don't care if they were the first person chosen. We don't care if they were the last person chosen. All we care about is, are they going to be part of the committee or not? So the order of choosing them does not matter. So in this case, we're dealing with combinations. And so the first thing I would do is just figure out what the permutation is. So we have 3 spots to fill. So the first spot, we have 8 choices. The second spot, we have 7 choices. And the third spot, we have 6 choices. So when we multiply those together, we get the number of permutations. And then all we're going to do is divide by 3 factorial, or 6. And look at that. Right at the end, we have 8 times 7 times 6 divided by 3 factorial, and that gives us 56. So there are 56 different combinations of getting a 3-person committee from 8 people. Okay, let's talk about ice cream combinations. Suppose that you select 3 different flavors of ice cream from an ice cream shop that carries 12 different flavors. How many flavor combinations are there? Now, again, the order in which you're choosing the flavors does not matter. All that matters is, does the flavor get on your ice cream cone? Doesn't matter if it's the first scoop or the last scoop. Okay, so again, we've got 3 flavors to choose. We got 3 flavors that we're going to pick out of 12 flavors. So we've got 3 spots to fill, right? So the first spot we'll have 12 to choose from, and then the second spot we'll have 11 flavors to choose from, and then the final spot will be 10 flavors to choose from. And then that's the number of permutations. When we multiply those 3 numbers together, 12, 11, and 10, that's going to give us the total number of permutations. But then we're going to divide by 3 factorial again, or 6, to get the number of combinations. And that's what we end up with. And so that gives us 220 different combinations of flavors for a 3-scoop ice cream cone, or in a cup. Now, probability and coincidence. Coincidences are bound to happen. They do happen, okay? So although a particular coincidence may be highly unlikely, some similar coincidence may be extremely likely or even certain to occur. In general, this means that the coincidences should be expected to occur with their likelihoods dictated by the laws of probability, okay? So it just depends on how likely these coincidences are to happen. So let's look at the probability that at least 2 people in a class of 25 have the same birthday, right? So we have a class of 25 students, and we want to know, hey, what's the likelihood, or what's the probability that at least 2 of the 25 students have the same birthday? So the way we're going to answer this question is we're going to answer it using the complement rule, because to calculate the probability that at least 2 people have the same birthday, we'd have to, that would be a lot of calculations. So it's going to be easier using the complement rule in this case, like I mentioned before. So if we have at least 1 pair of shared birthdays, we're going to do equal to 1 minus that there are no shared birthdays, okay? So that's a much easier calculation to do. So let's find the probability that none of the 25 students have the same birthday. So how many days are there in the year? There's 365 days in the year. Now, if we assume that births are random, right? And any person could have been born on any one of the days in the class, right? If we just, it's a random class, right? Then the first person, in order for everybody to have a different birthday, right? We would calculate the fact that, hey, the first person would have how many days to choose from? Okay, the first student is going to be born on one of the 365 days. Once the day is chosen on that one, then the next student will only have 364 days to choose from as a birthday. And if we do this, we're going to have all 25 students that will have, again, if we do the permutations, right, we're going to have 365 times 364 all the way down to 341. That's going to be the total number of different arrangements of birthdays for 25 students that do not have the same birthday. Okay? So the top number will give us the total number of ways that 25 students can have different birthdays. Now, the bottom number is the total number of possible outcomes for 25 students to be born on any day, right? So this allows for everything. So how many different ways of the 25 students are there? Well, if we allow that all 25 students could be born on the same day, and we allow for having the same birthday or any number of students having the same birthday, then we're going to say, hey, there's 365 possible outcomes for each and every one of the students. So that's going to be the multiplication. That's going to be the fundamental accounting principle. So all we're going to do is, since we have 25 students, we're going to do 365 times itself 25 times. So that's going to be equal to 365 to the 25th power. Now, why does it start on the top at 364 and not 365? And why is 365 to the 24th power and not the 25th power? Because one of the 365s in the numerator cancels with one of the 365s in the denominator. So that's why we end up with this. Okay? Now this gives us the probability that none of the students will have the same birthday, which is going to be 0.431. And so now if we use the complement rule and we use 1 minus that, we get 0.569. So there is a 57% chance that at least 2 of the students will have a shared birthday out of a class of 25, which is pretty high. Higher than you might think or might have thought. All right, that's it. You have a great day, and I'll see you next time. Again, get help, practice. This is probability and all these counting principles. The practice helps improve, okay, your skill. Have a great day, and see you next time.